Okay, thank you. Okay, so jumping right in, I want to introduce the organizers of the event today. Obviously, there's me. I'm standing up here first, but I'm not the only one. Dimitris, Timo, Joachim, Ahmed, and Maureen have all put a lot of effort into this, and you'll be hearing from all of them throughout this, in addition to many other people. These folks are all experts in 3D human body modeling, and SMPL in particular, and they have a lot of wisdom to share about what's easy, what's hard, and how to make things work. The structure of the tutorial is, as I said, everything is going to be recorded and then made available afterwards so that everyone who couldn't be here is able to take advantage of this. So this is online format's a little bit of a challenge. We couldn't quite figure out how we would do a real online tutorial demo thing where you interact. So it's going to be mostly a series of presentations with questions. There are already a bunch of good resources on the web. There's my department, Perceiving Systems, has a code page listed here, and Meshcapade has now put together a SMPL wiki page, which is compiling all kinds of useful information. And there's going to be, in addition to the talks, there'll be slides and other links made available after this tutorial on the SMPL Made Simple page. So you can just follow that. Now the day, it's an 8-hour tutorial, and it's divided into 2 sessions. The morning session, it's actually afternoon here in Germany, but the morning session for some of you is about really introducing you to SMPL, including the history. You should go away from this knowing the history of 3D body models, all of the terms that maybe you hear thrown around. What's some of the stuff we struggled with? How did we do things, and get some insights? You should go away with also resources and things like data sets, and also how to use SMPL in various graphics packages. We get a lot of questions about this. And in addition, we'll try to answer the most frequent questions we get, and hopefully plenty of time for discussion. We'll adapt this morning session as need be to finish on time with time for questions. And that's followed by a so-called afternoon session, which will be late at night for many of us. That has experts in the field who will be giving presentations on current state-of-the-art methods that use SMPL, applications of SMPL, and SMPL in industry. So I think it's a pretty exciting session. If you've already had a chance to watch some of them, there's a few talks on there, like the Microsoft talk, which is really a spectacular talk and super exciting. So stay tuned for the afternoon session. Stick with us. So any questions before we get started here? About the day, what you're going to learn, anything else? I can't see the chat, so shout out if you have questions.
No questions so far on the chat either.
Okay, if there's no questions, then I'll just dive in, checking the timing. We're 2 minutes ahead of schedule, but I suspect that's probably okay. So what is this all about? We've got this is a tutorial on using the SMPL body model and what it is. But why is it there? Why did we create such a thing? And we're motivated by the fact that humans interact with each other and the world through their bodies, through their facial expressions, through their contact. And we engage with each other by gestures and expressions. We make social contact with each other through touch, from shaking hands to hugging and dancing. We interact with the world by manipulating objects. And of course, we do that through our hands and our feet and the rest of our body. And we cooperate with each other in ways to solve problems. And all of these complex uses of our body are things that we would like computers to understand and to reason about. And we would like computer graphic systems to be able to generate or to simulate. So the goals here really are 2 intertwined sets of goals. One from the computer vision side, which is about training computers to see us, to understand our behaviors, our emotions, our actions, and our interactions with each other and the world. And the other direction is more from the graphic side, or this includes augmented and virtual reality. And it's about training avatars to mimic us. Somehow by watching us, seeing us in videos and so on, to learn how to behave like us. With the idea that if we can reproduce something like human level behavior, then we'll have understood it at some level, a computational level at least, which I think would be quite fundamental. But why is it difficult? So it's difficult for lots of reasons that you probably know. So we're often given 2D images, so we lose the sense of 3D. So we need priors or something to help us deal with that. The human body is highly articulated, it's high dimensional. There's a lot of self-occlusion. People wear clothing that makes their contrast low and so on. People's body shape varies tremendously. From little children to sumo wrestlers, and people wear complex clothing. They stick their heads in kayaks and adopt all kinds of weird poses. So the problem of understanding humans and the behavior is rich and difficult. So I want to just take you through a little bit of the early history, like how people thought about this problem. And it really goes back to the beginning of photography itself, with the work of Muybridge and Marais. This work by Marais here is very prescient. It was some of the very first photography, and it was used to study how humans move. And we're still using photography to understand how human move today. But a psychologist named Johansen had kind of a similar idea to Marais, where you could see the dots, maybe, and Marais put reflective dots on people and then took time-lapse photographs of them. And Johansen had this observation that if you put point light displays, markers on the body, and then played them in motion, that people could actually perceive what was going on, that you could recognize things like walking, running, dancing, etc., from as few as 10 to 12 joints. Now, Johansen ended this quote from his paper with the etc. And of course, everybody took that to mean and everything else. And I sort of took it to mean those were the only things he could really think of that worked. Because there's a lot of human behavior that's much richer than the motion of just a few joints. And we'll see that. So Johansen was brilliant in many ways, and this was inspirational work, but it did kind of lead the field, I think, in sort of the wrong direction for several decades. And in fact, most of the work in the field has focused on Johansen's idea of recovering the joints of the body, just a few sparse locations. Now this, I don't mean to criticize OpenPose. I think it's one of the coolest and most influential pieces of software in the field in the last decade. And it's certainly groundbreaking. But it takes this same paradigm of let's get the joints of the body out. And so I want to ask, are the joints enough? The joints, it's interesting that we focus so much on joints because we never actually see them. Okay? Hopefully, you never actually see somebody's joints. They're hidden, they're inside the body. And so they're not even observable features. They're implicit somehow. And what they don't allow us to do is to reason about contact, because the joints never touch the world. It's the skin that touches the world. And so if we want to reason about contact between people and objects, hands and cups, people hugging, we actually really need to reason about the whole surface of the body, the outside, the part, and that's the great thing about that, it's the part that we can actually see. It's not invisible. And this is actually also important, the shape of the body, for many other things, for example, human health, and actually even how we perceive each other. Our body shape plays a major role in that. So the argument is that we really want to understand the outer surface of the body. Now, that's not a new idea. The very, very first work in this field, I think, was the work of Ram Navacha and Tom Binford at Stanford in 1973. And Navacha was a PhD student, and Tom was interested in modeling geometry, and he had these techniques called generalized cylinders. And so they had the idea of modeling, here it's a toy, it's not a real human, it's a doll, with a collection of generalized primitives, these generalized cylinder shaped primitives. And they fit it to range scans, which today, of course, you just go pick up a Kinect or some other range sensor. But back then, those things just didn't exist. So they actually had to first engineer and build one of the first range scanners so that they could fit the data to it. It was much harder to be a PhD student in 1973 in computer vision, I have to think. And Mara Nishihara took this idea, further generalized it, and came up with more of a framework or a theory of how one might represent complex objects as a set of articulated primitives, like the ones on the left, which characterize maybe a human and with a variation in the shapes of the parameters, maybe a chimpanzee or an ape or something, right? So that's the early work. And the first work to actually relate this to images was the really groundbreaking work of David Hogg in 1983, where he took images and he did what we did in those days, which is he ran an edge detector on them and found the edges, and then he fit his model to it. And this is what he got out. So a monocular sequence, which Andrew Fitzgibbon managed to pull out of the paper and turn into a movie. But it shows you the very first work on using a 3D human body model to analyze a video sequence. And what would that 3D body model look like? Well, it looked like this. It was a bunch of hand-coded descriptions of some primitives and their spatial relations to each other and how much they could rotate relative to each other and so on. It was very much a handcrafted model. And then after this really groundbreaking work of using 3D models to understand images, nothing happened. An entire decade went by and there's basically not a single paper on this topic. I think Hogg scared everybody off. Nobody could really reproduce it. It was probably way too hard for the computing power of the time. And nothing happened, literally for a decade. But then it picked up again in around the early 90s, all based on this classic idea that the body is represented as a kinematic tree. So there's a root with some translation and rotation in the world coordinate system, or maybe in the camera coordinate system. And then relative to that root, we have parts that undergo a relative rotation, here represented by these thetas. And then each part may have a different kind of articulated structure relative to its parent part. And this is how we represent a body, a bunch of shape primitives, a bunch of a kinematic tree that's positioned in the world and then articulated. And then if you know the camera, then you can project this into the camera views, one or more views, and then match it to some features. This is the classic approach. And then, so basically after around 94, 93, 94, things picked up again. People were able to replicate the work of Hogg. There was a bunch of nice stuff going on. And then people realized that they needed something maybe a little bit richer for shape than just a bunch of cylinders. And the first work on this, I think, was Pentland and Horowitz, where they represented a Tin Man, which oddly in this case was actually well represented by cylinders, but they represented the body here with superquadrics. That idea was pushed further by Dario Gavrila in his PhD thesis, where he used these shape primitives to capture the shapes of different people. Notice there's a man and a woman here, and they have different body shapes. And he used a multi-camera system to track them around. And then one of the really seminal pieces of work, I think, was the Bregler and Malik work on twist and exponential maps. And that representation of body pose is one that people are still using today. It's a very nice paper. Now, one more little piece of history because none of this is based on machine learning yet. This is all based on handcrafted 3D models. So when did learning come in? And I think it was this paper by Bomberg and Hogg at ECCV in '96. At least it's the first paper I know that tried to represent the body using machine learning. Okay, and so what did they do? They did it all in 2D, and they had these contours of people from silhouettes walking in from different points of view. And they took these and they put them in a canonical representation, and then they do principal component analysis. Yeah, so I see there's a question. Go ahead. Shri Karan, if that's right. You want to ask? Ask to unmute. Well, if you want to ask a question, just shout it out, and I'm happy to answer. All right, so what's the problem? So the problem was that humans don't actually look like this. The models don't match the data. And people are trying to match these models to image features. And the image features were, wiggly lines, and these were all like cylinders and stuff. And so all the systems people built were highly brittle. And so people made complicated priors and all kinds of things to make them work, and they still didn't really work all that well. And so in my group, I was at Brown at the time, we were thinking, well, what we need is actually a better model of human body shape. And this actually emerged in a collaboration with Intel and Horst Hauseker's group there. Before I get to that, there have been other people who have been really trying to push this in different ways, different representations of the body. That early Gavrila thing, Christian Smichinescu in his PhD thesis used something similar, and it worked really well. He also, I think, was the first person to have a differentiable solver for that, which I thought was pretty cool at the time. Nobody else could do it. And then Terzopoulos and Metaxas been working on this, and Fua and Plenkers had this metaballs model of the body. But none of them were really very realistic. They were kind of handcrafted, and then a miracle occurred. The big breakthrough came not with human bodies, but with faces. And it came about through this work by Blance and Vetter, the famous work on modeling face shape. They were actually here in Tübingen, where we are, and captured 3D face shape with this, a scanner. And then they learned a statistical model of the body shape and the appearance. And as far as I could tell, 1989 was the first time a 3D body scan of a person was made. So that wasn't all that long ago, quite honestly. And in the seminal paper by Blance and Vetter, they just focused on the face. They used principal component analysis to build a shape space of faces and their appearance. And then they could take an image, and they could, using an optimization-based approach, solve for the shape of the face, the lighting in the scene, the albedo of the face, and its pose parameters. And it was really quite a groundbreaking and inspiring piece of work. So the natural thing was, when I started thinking about this, well, let's do that for bodies, of course. But why is it hard? The body's actually a lot harder than the face, and it's sort of a trivial proof, because the body includes the face, so for sure it's harder than the face. But it also includes 600 muscles, 200 bones, and about 200 joints. People actually argue about how many joints there are in the body. And those joints have many different types, different degrees of freedom. In addition to that, we bulge, we breathe, we flex, we jiggle. Our shape changes throughout our lives. It changes based on how much we work out and what we ate for lunch. And the inside of the body is pretty complex. And I think it's super fascinating to try and infer all of what's going inside the body, but we're not going to do it. We're going to treat that as too hard, and we're going to focus exclusively on the surface that we can measure. So to make that feasible, this technology for face scanning had to get extended to scanning of the body. And Cyberware was the first company to do this that I know of. And using this Cyberware scanner, the US Army conducted something called the CSER survey. They made a data set of scans of about 2,000 men and 2,000 women from the US and Europe. Now, they made this sometime around 1999. It was published in 2001. And it's important that they based the demographics, like what are the ages of people? What are the ethnicities of people? What are the weights of people? They based this all on a 1990 US Census data. And since 1990, the US has become much more ethnically diverse, much, much heavier. And so the CSER data set is representative of a snapshot in time, and not even 99 to 2001, but really 1990, okay? So it's a bit out of date. But still, it provided several thousand full body 3D scans. And the first people to notice this and really pick up on it right away was this Brett Allen, who was a PhD student with Brian Curlis and Popovich at University of Washington. And they took Caesar scans like the ones you see at the top here. And they took a template mesh and they registered this template mesh to each of the scans. And they did the same thing for female scans. And so they brought them all into a common frame of reference with a common topology, a common mesh. This was actually pretty hard. They proposed a solution for doing it. They didn't actually do it to the whole Caesar data set. They only did it to a small portion of it because it really was a very difficult problem at the time. And, but what they were able to do then is use principal component analysis to build a shape space. There were some problems with it. It didn't factor out pose and shape, and we'll talk about that later. But they could then interpolate between bodies, which is shown on the top here. The red outlined ones are true bodies from the Caesar data set, and the ones in between are linearly interpolated or morphed in this PCA space. They also rigged these models with a skeleton and animated them, but you can see that it doesn't really work out all that well because they didn't model anything about how bodies actually move and deform. But this was really pioneering work already in 2003. The next big breakthrough came in Drago Angolov's PhD thesis at Stanford, and this was called SCAPE. And he scanned a bunch of people in different poses. So then he had people it was only one person in different poses himself. And he had a bunch of PhD students in a single pose. And then he put these two things together to learn a model that could deform, change body shape, and could change pose. And it was pretty cool. Interestingly, it was based on triangle deformations. And we're going to talk about a simple, which is based on vertices. Triangle deformations have a whole bunch of problems. It was over-parameterized. There was no skeleton to this. There were no bones, and the lengths of the bones weren't consistent. So you could repose the body and its shape would actually change. But it was super inspirational work, and it affected everything that followed it. This was the sort of the source of inspiration for everybody that came after. Brett Allen actually, this looks bad, but Brett Allen proposed a model in 2006 where he could change the shape of the person and its pose. And it was formulated really, really quite properly. It was a good model. He just didn't have the training data to do it. It was a little too complex to optimize. He didn't have the training data to do it, but he was really on the right track in 2006. So we built our first SCAPE-like model in 2006, I guess, 2005, 2006. And then the first paper I think that fits that to images is this one at CVPR 2007. And we showed that by using a 3D body model of a human that better matches the image evidence, we actually got more accurate 3D pose estimation. So that got us excited that maybe we were on the right track. There was a flurry of interest in building such models, and I won't review them all. Nils Hasler from the NPI for Informatic had a bunch of different attempts at this and did some really interesting work in the space. And then Microsoft also tried to build one. They called it Tenbo, which was a tensor-based model, which I don't think is being used anymore. I think the idea here was to model correlations in body shape and pose, but you need a lot of training data to do that. And I suspect they didn't have quite enough. All right, so that's the history. And I want to, based on that, I want to take us into the present. And the goal here is to build virtual humans. So here are some virtual humans based on simple. I think you'll agree they look more realistic than what we were just seeing. And our goal here was really to define a very simple, and it's not a surprise that SMPL, we pronounce it simple. It was designed to be simple. We had a SCAPE model before. Actually, we had an improved SCAPE model called BlendSCAPE. It was complicated, it was hard to optimize. These triangle deformations, the triangles were all moving independently, and then you have to do a least squares solve to bring them all back together. It was too complicated to really plug into anything. It wasn't compatible with any graphics packages out there. No one really wanted to use it. It was not going anywhere. So we went back to first principles and said, okay, let's build the simplest model we can that's compatible from the ground up with standard graphics tools. This was an absolute must. It also had, oh,
there's a question from somebody asking, what do you mean by fits to data?
Yes, is it in here, fits to data? Yes, I will talk about what that means. So an example of fitting to data was this. So we had here a silhouette, for example, and we wanted to fit the model to it. So that means we should be able to, in this case, we should be able to differentiate the model with respect to the image. So we should be able to optimize easily the pose and shape of the model to fit image observations. Now the data might be 3D scans, it might be RGBD, it might be images, it might be joint locations, it might be 3D mocap markers. But basically that, I guess what I mean by fit to data is it should be differentiable and low dimensional to make it easy. Oops, I don't know what's happening to my screen there. Did that answer your question? Okay, it should also look like real people. There's no point having it if it doesn't look like real people. It should move like real people. That's a tough one. And so we set out with these goals.
Thank you.
Oh, you're welcome. So but we were missing something. And that is the cyberware scanner and all the previous scanners. You had to stand still, and it took about 12 seconds to get a scan, and you tended to wobble. You had to close your eyes because there was a laser, and then you tended to wobble. And so the scan, it was hard to scan people in complex poses, and you couldn't scan people in motion. So when I joined Max Planck, I went around looking for companies that could build such a thing. And 3DMD told me they could build it. And the spec was, you had to have somebody like a 6 foot tall person who could stick their arms out to the sides and over their head completely and jump around and wave their arms in this space. And we had to be able to capture the 3D body. We had to be able to scan it at 60 frames a second. That was the spec. And nobody had such a thing before. And this is what the device looks like today. And this is what the raw data looks like. So there's 66 cameras, 22 color cameras that capture the texture, and 22 pairs of stereo cameras. There's a speckle pattern that's projected on the scene to make the stereo work better. And then that alternates with white light LED panels. And then you see a raw scan on the right-hand side. So that's a 4D scan. It is a 3D, bunch of 3D points captured at 60 frames a second. So that opened up everything for us, because now we could take our data with thousands of people, say from the Caesar data set, and then capture them in a huge variety of poses very quickly, doing all kinds of things. And as you'll see, also capturing soft tissue motion. So from this, our goal is then to take thousands of scans and to learn a function, M, that takes in some parameters, theta for pose, beta for shape, delta sometimes for soft tissue displacements, and possibly appearance, A here. So we'll talk about this. We'll focus on theta and beta for the rest of the talk. So modeling bodies. What is a body model? So we represent the body model as a 3D triangulated mesh. Choosing a good mesh is a key thing. So our mesh is designed such that men and women have the same topology, allowing a nice interchange between them, or as many of people use our neutral body models, gender neutral ones. So that was a design choice to have it gender neutral. It had to be, this was artist designed and went through many iterations to get a mesh that made artists happy with it. Because if artists weren't happy with it, they weren't going to use it. And it could probably still be improved. The mesh is segmented into parts, and there's a kinematic tree, and the parts can rotate relative to each other in a kinematic tree, just as I suggested for the old-fashioned models. So the simple mesh is about 7,000 vertices. These are points in 3D space, represented each by 3 numbers, of course. And that means a body is 21,000 numbers. Okay, that's a body. The problem is most settings of 21,000 numbers don't correspond to anything in particular people. So the whole game here is to characterize which settings of 21,000 numbers correspond to real people. That is, we want a function that takes in low-dimensional pose and shape parameters and outputs 21,000 numbers that correspond always to a real body. And the idea we're going to follow is based on Anguilov's model of scape. Simple is based on that same idea, and that's the idea of factoring. So we're going to take a mean template shape T, and we're going to factor changes in pose. So you see at the top here, a woman changing pose, but her identity should always be the same. She should look like the same woman, even though her pose is changing. Okay? So that, if that's true, then we factored pose from identity. Okay? And then, of course, we want to, at the bottom here, be able to change identity. And you see the model is going through shapes of different women, but the pose should always be the same. So you shouldn't see the pose change. And then we want to be able to compose those two things on the right so that pose and shape change simultaneously. And we can represent then any body shape in any pose. This factoring is really key because it simplifies learning and inference, and it simplifies its use in graphics packages. So again, we're going to call pose theta and identity or shape beta. Okay? There's other types of shape. There's going to be pose-dependent shape variation as well, which is separate from identity-dependent shape. But
I had a question.
Yeah, sure.
Why do you say that in the third one, identity is preserved, but not in the other two, that is pose and shape plus pose?
Oh, and shape plus pose identity should be preserved as well. So we're just, what you're seeing on the, we're changing both identity and shape simultaneously just to illustrate that we can do that. So the thing on the right never could happen in real life, right? It's
okay, thank you.
Shape shifting. Thanks for the clarification. And there's other kinds of factors that we've explored. For example, breathing can be layered on top of this, and dynamics, soft tissue dynamics could be layered on top of this. There's a key difference between the SCAPE model. SCAPE was a multiplicative model of deformations, and Simple is an additive model. And there's pros and cons to each of those, but the additive model is particularly simple. Now there's one big problem. So now we've got thousands of scans, and we've got some idea that we want to learn this mathematical model that captures and represents them. But scans are not models. They're just a collection of unordered 3D points. And so the very first step of building a body model is to take a template mesh in pink here and bring it into alignment with each of the scans S sub I. So on the right, you see in blue a scan, and this is, we call this either, confusingly, we call this a registration, the pink thing, or an alignment. And we mean the same thing when we say registration or alignment. And it should match well and really tightly. And when it does, you see this very fine overlap between them. Now, why is this hard? It turned out, sometimes in science, the least sexy things are the hardest. And everyone thought this problem was solved in the 2003 paper by Brett Allen et al. And we implemented that, and it didn't generalize. And it turned out to be a really hard problem, and one that nobody really wanted to publish because everyone thought it was already solved. And there's several things that are hard here. First of all, the resolution of the body scan that you're trying to match is very different from the resolution of their template mesh. They may have different features that aren't present on the template, for example. The other thing is the body has lots of smooth areas that it's not clear if I'm trying to match between one person and another person, what's the exact point that corresponds on the belly or on the arms between these people. Maybe the belly button is kind of obvious, but other parts are not so obvious. And then human poses are really complicated. Often in scans, there's missing data. You see that in many of the examples here, particularly in the feet, or if somebody's a little bit outside the scanning volume. And when there's self-contact, all bets are off. We actually have a paper called Touch that deals with self-contact alignment at CVPR. So the idea that we used to solve this was something we called co-registration. It appeared at ECCV in 2012. And the idea was, look, if I already had a good body model, this problem would be pretty easy. I'd fit it to the data. I'd use the body to figure out the pose and shape. It'd be robust to missing data. That would be pretty easy. And then we could just refine it by looking at how it deviated from the scan. But the problem is we needed the scan and this alignment to build the model in the first place. So we had a chicken and egg problem. And whenever you have a chicken and egg problem, one thing you could do is jointly solve for these things. So we solved for a model that aligned the meshes best. And then we solved for the alignments that produced the best model. So I'm not going to go into the details here, but this process worked relatively well. There's a lot of other little details about searching in the pose space and using a prior and so on, but it proved relatively robust. Still, this is, I think, one of the harder parts of the whole problem, which is probably underappreciated in the field. Okay, in the chat, I see 4 things, but have we answered all of them? Okay.
There's no new questions.
Thanks. If you want some data like this, the Faust data set contains 300 real scans of 10 subjects in 30 different poses with ground truth correspondences between them. And so that's one source. If you want to start playing with some 3D scan data, you can check out Faust.
So we got a question, Michael.
Sure.
It's a question. So initializations and priors would be a key factor in optimization, right? I think this was related to registration.
Yeah. Yes, indeed, you can get stuck in local optima. Honestly, our processes for aligning scans have changed a lot since deep learning. What we do now is we have a deep learning front end that gives, from which we get a rough initial pose and then we refine it. So once you're in the ballpark, you can do classic optimization, so the idea is the front end, the deep network gets you into the right local optimum, and then you can really refine it. Nothing beats the refining it through an optimization technique at the end to get. So this is just some examples of alignments or registrations to some particularly challenging bodies in Caesar. These are real women. This is, this is how people look. There's some things here you might think of as artifacts. I've looked at the scans, they're not artifacts. This is really how people look. And they're really, it's really, really hard to do at this level of detail.
Thanks, Michael. So the second question, how many body scans are enough? And when do you know you have enough versus need more variety of scans?
Yeah, it's a great question. So Ahmed who's answering this question or posing the question right now, will have a talk, the very last talk of the tutorial. He'll talk about everything that's wrong with Simple and training, how training on 2,000 men and 2,000 women based on the 1990 census is not enough. And he trains on another 10,000 to get a better shape representation. There's a lot of things to take into account here. And he'll bring this up, that all of the women here are wearing a particular kind of sports bra, so there's not so much diversity in bra type, which would happen in the real world. And so there's all kinds of, the answer is 4,000 is not enough, in my opinion, to really capture the diversity of the population. And you can see that as you get heavy in all kinds of different ways. The way your fat goes on your body, it varies hugely between people, whether you carry it on your legs, your waist, your hips, your chest. And so there's just a tremendous amount of variability and variety in the human form, which makes it an interesting problem.
So there are 2 more questions, Michael,
Sure.
to clear all the questions. So what are pose priors? So you mentioned pose priors. during your talk?
It's a great question. So there are some poses of the body that are impossible. There are some poses of the body that are possible but unlikely unless you're a gymnast or a yoga teacher. And then there's some poses of the body that are highly common. And a pose prior just gives a probability distribution over that parameter theta, the pose parameter, which we'll talk about, across the whole population. And that's very useful for many things. And there'll be a presentation later on a particular pose prior called V-poser that's learned from a large data set. So stay tuned for that. Nima Gorbani will talk about V-poser later, I believe. And it'll probably come up in the talk by Dimitris as well.
Right. And what happens when you don't have data for a certain body type? Does this generalize, like, do the model generalize to?
It's a great question. So as we'll see, if I get to it, we learn a linear model. Linear models are particularly good at generalizing, particularly if the space is actually linear. So things do generalize, but of course you can only generalize so far if you've never seen. So for example, in our data set, we don't have children. Children have very different body proportions than adults. They have a much bigger head relative to their body. And variations in the adult form do not explain children and their shape variations. So it doesn't generalize to children. We have a fix for that at CVPR this year in the Agora paper, where we add, we combine an infant model with an adult model to get an approximate child model.
That's
so
all.
stay tuned for Agora. All right, I'm running way behind. So I'm going to skip, I promised you 4D scans. But maybe I'll just skip over 4D scans because we're not going to have time. So I'm going to jump up. It'll be on the slides. I'll put all the slides on the web. So now we have this shape training set with 2,000 meshes per gender in correspondence with a single template mesh. And a very important point is they're all normalized to the same pose. I'll talk about this later. I'm not going to tell you right now how to do that because you have to understand something else first. But it's critical that they all be in the exact same pose and not approximately. Once you've done that, you can actually do statistics. Remember, we just have, a body is just a vector of 21,000 numbers. So we could do things like compute the mean vector, and that gives us the mean body. Here's the mean man and the mean woman across the US and Europe. And they look kind of average. So, and then we're going to do statistics on the body. And you, probably in your very first class on probability, maybe in high school or even earlier, somebody probably taught you about the normal distribution, or as we call it, a Gaussian distribution. And probably the first example they gave you was something like human height or human weight. And here's examples of height and weight fit by normal distributions. It's kind of a classic model because humans grow kind of linearly, and then there's the variation of the population is kind of Gaussian distributed. It's not entirely true because obviously you can't be negative height and negative weight, and you can't be infinitely tall, but it's roughly Gaussian. We're going to take advantage of that. So what we're going to learn is a statistical model of shape. So we're going to start with this mean body shape. Here we'll start with, look at men just for simplicity here. They're all in the same pose. We have each body represented as a 21-dimensional vector, and we want to compress this into a low-dimensional space. Of course, we could use a fancy non-linear deep autoencoder, but we don't have enough data to do it, and we don't need to do it. Alex will show you why. So the simple thing to do is you just vectorize the bodies. So now we have these 21-dimensional vectors. We've got n training bodies. We subtract the mean from each of these. And because everything here is living in a Euclidean space of points, because we factored out the nonlinearities of body pose, we could just put this into a matrix and do principal component analysis on it. Principal component analysis finds the eigenvalues and eigenvectors of this matrix. The eigenvectors describe the major directions of variation in the shape space, in the space of bodies. If we take the high order eigenvectors, that gives us a low dimensional linear subspace U here. So we often take between 10 and 300 of the principal components. Remember that here I had 2,000 men. So we're going to take maybe 10 principal components to represent 2,000 men, which is pretty good compression. And then a body shape is represented by the mean mu plus a linear combination of these eigenvectors U. That is, we multiply them by these things we call beta linear coefficients. They're just, in the case of, if you're using 10 components, it's 10 numbers. So a body is represented by the mean and 10 numbers. And with that, we can approximate any body shape in the space and it can generalize. So is there a question? Okay. So what does this shape space look like? Here are the first 10 principal components of the female shape. And we're taking them between plus and minus 3 standard deviations from the mean. The nice thing about PCA is it gives us a Gaussian distribution over body shape. You can think of that as a Gaussian prior over body shape. Now what you should see here is the shape of the person changing. This is capturing the correlation variation of the body across the female population. And here's for the men. Now what you should notice is that the pose shouldn't change, just the shape. So this is pure shape variation. Now, of course, there's ambiguity there. If somebody has a hunch, for example, is that a posture thing or is that their body shape? And it's a little ambiguous. It's not actually properly defined. But here, this should look like pure shape variation to you and no pose variation. It's pretty much true. And that's the case if it's well factored. Once you have such a thing, then we could just do simple body math. You take the average body and you take some amount times the first principal component plus some amount times the second plus some amount times the third, and then you get a new body out. That's simple. That's a simple shape space. And if there's pose isn't involved, that's all there is to it. It's really simple linear math. All right, and this PCA space captures, this is the first 30 principal components, which capture like 98.5% of the variance or something like that. People typically use 10. We make available 300, and nobody needs more than 300. You really capture all of the variance effectively in the data using 300 components. So what do these look like if you project the actual samples of men and women into, here's the first 3 dimensions of the PCA space. You see they form blobs that are kind of like 3D Gaussian blobs. This is pretty nice. If you take men and women separately, obviously you put them together, they have different means because they're different heights and different weights and so on. But this is just a hint that PCA is actually a pretty good model of body shape. So shouldn't I use something fancier? My answer is no. PCA is actually really good for this. You know, if you say simple with 10 components just doesn't capture enough detail, and I've got some fancy nonlinear model, well, you know, how big is your latent space or how many parameters are in your model? I mean, you can just add another component to simple and you get more. It's very, very compact. It's very hard to beat. When something's actually represented well by a Gaussian distribution, it is very hard to beat PCA because it can work with very little data. That's my pitch to you, that old models sometimes are the right models. So moving on to pose, we have, for the original simple model, we used 1,800 registered scans of 60 different people. This is what they look like. And now I have to tell you a little bit about body models. Is there a question before I go on?
Yeah, so there's a couple, but someone needs to mute.
I think I can mute them.
Yeah, so first is like why there isn't plenty of bigger data sets than the Caesar data set. Mm-hmm. And the second is a question about it's very hard to impose the exact same body pose in practice.
Correct.
Do you do some pre-processing like small non-rigid deformations?
Yeah, it's great questions. Both great questions. So the first question is, there are larger data sets. They're commercial ones. People do big sizing studies for, in the clothing industry, they do this. They're very, very expensive to run. You have to set up a scanner. You have to recruit people. You have to bring them through. You have to get their consent. You have to have people come in and they strip down and they put on stuff. People don't really want to do it. It's non-trivial and very time consuming and expensive. So this is why there's not a lot of such data sets. There are no, apart from the data sets we make available like Faust and Dynamic Faust with 3D scans and CAPE and a bunch of other ones, Buff, we'll talk about data sets later. I know of very few public data sets. You have to buy them. Caesar, you have to buy. Size USA, you have to buy.
Yes.
And then the second question, now I forgot, was a good question.
It's about pose, so it's very hard to impose.
Yes, right, right, yes. Good point. You have a very good point. I'll get to it, I promise. Hold that thought. We have a technique to factor out pose, and but I can't teach it to you yet until I do something else first. I have to still introduce the simple body model. For people keeping track of time, we'll probably cut one section on data sets because it's already on the web as a video and you could just watch it because it wasn't going to be presented live. So I'm going to run over here. I can see that, which is fine. All right, so I have to explain standard skinning to you if you don't know about it, and because it's the core of everything. So this is what's used for most character animation. So we're given a template mesh T with some number of vertices, N. We have joint locations J. So we have K of those joints. We're given some blend weights, which is a matrix of the size of the number of vertices times the number of joints. It's illustrated here in a color-coded way. I'll talk about that in a second. And then we have pose represented by theta, and with K joints, we have rotations theta. We have 3 numbers for each joint, okay? So what a skinning function does is it takes the template, the joints, the blend weights, and the pose parameters, and it produces vertices, okay? The most common one, and basically the simplest one, is linear blend skinning. You'll see it everywhere. It's where vertices in the final posed mesh are determined as a linear combination of transformations from potentially all the joints in the body, but controlled by the blend weights W, K, I here. So K is indexed over the joints and I is indexed over the vertices. So this typically means that a vertex near a joint, say the elbow, is going to be influenced by both the lower arm and the upper arm, for example. It's in its final location. Now, linear blend skinning is really simple, but it has some well-known problems. So it doesn't preserve volume, so it tends to collapse, like on the left-hand side. And on the right, if you rotate things, sometimes bad things happen, and it's called the candy wrapper effect. So it has a bunch of problems. And so what people in the industry do, so in Hollywood or something, they take a body like the one on the left, they pose it using linear blend skinning, and you see all kinds of artifacts at the elbows and the hips and stuff. And so an artist goes in and sculpts a 3D displacement to the original mesh. So they do that such that when you pose that mesh, it looks like the thing on the right, which looks right. So let's go back and forth between that. So original body, deformed body. When you deform the body in the rest pose and then pose it, it looks good. If you don't do it, it looks bad, okay? And so this is what artists do, and they spend a lot of time doing this. So our idea was to automate that. let's just learn those displacements, okay? And so standard skinning takes blend skinning function W, template, joints, blend weights, pose, and gives vertices. The simple model is this. It's a function M that takes theta and beta, pose and shape. It takes blend skinning function W, but rather than taking a template, a fixed template mesh, it takes a template mesh that's a function of body shape and pose, okay? That's going to be critical. And the joints are going to be a function of the body shape. And then some blend weights and the pose, of course, right? So that's the difference between standard skinning and simple is just that the template mesh and the joints are going to be a function of some parameters, body shape and pose. Okay, so here's a template mesh with learned blend weights and white dots corresponding to the joints in this rest pose, the T pose. When we add blend shapes, this is our principal components that you saw before, the body shape changes, and notice that the joints are changing with the body shape. This is critical. So we have to learn a function relating joints to body shape so that we can change the shape. Then given a pose, like the one on the far right, we're going to learn pose correctives. So you see pose blend shapes. If you look carefully, you'll see this later also. The body shape is changing as the model is being reposed. And we're going to learn that function as a function of the pose of the body. Okay, so let's just focus on pose for a moment. Forget body shape. We've got this linear blend skinning function, and we have a template mesh that's a function of pose theta. Now, that is going to be an additive. Everything in simple is going to be additive. So we're going to take the template mesh T that we had before, say the average man, and then we're going to add some function BP of theta to that, okay? And so what should BP be? So we want to keep everything linear to keep it simple. So it's going to be a linear combination of some posed blend shapes. These are just going to be a vector of 21,000 numbers again. Okay, and some people call them pose correctives, all right? And it's going to be a linear combination of these pose correctives, and we need some function of the poses that will combine these. And people have tried various things. There's radial basis functions, all sorts of stuff. The simplest thing you could imagine doing, just as an argument, would be to just take f of theta to be theta itself. So I index that by theta I take the ith rotation, and I multiply that by p, which I have to learn, and that would not work, it turns out, and I'll show you why. Making the correctives a linear function of the joint angles doesn't work. So what we did instead, and this was a key thing that made simple didn't work until we did this one thing. Instead of making the pose correctives a function of theta, the elements of theta, we made it a function of the elements of the part rotation matrices. I've jumped ahead a little bit here, but each part is going to be represented by, in the pose space, by a rotation matrix, which is 9 dimensions. So, and so then this is how in simple you end up with 207 blend shapes. You have 9 times the number of joints, which is 20. I don't know, I'm getting 207, but whatever. And what this does is it makes the blend shapes non-linear in the pose parameters theta. And if I'll show you what this looks like. So here on the left is a posed model after applying the blend shapes. And what you see on the right are the pose correctives happening. And what these are doing they're doing 2 things. One is they're correcting mistakes of linear blend skinning, because linear blend skinning is just an approximation and a pretty crappy one. And so you see that at the elbows in particular. But the other thing that's happening is this woman's body actually does deform as she moves. And that's a natural thing. And the pose correctives are learning those natural deformations as well. So these pose blend shapes have sort of a dual purpose. Now, this is a comparison of simple on the right with taking that function f of theta and just using theta on the left, and you get a volume collapse as the neck rotates. It doesn't work properly. And there are other solutions to this, but this worked for us. Is there a question, Ahmed? So you pop on.
Yeah, go ahead.
Is there a prior distribution about theta for each joint?
It's a good question. We've had many prior distributions from joint angle limits to a prior distribution learned using mixtures of Gaussians, which wasn't very good, or a single Gaussian, which is even worse. But stay tuned for VPoser, because that learns a nice, using deep learning, it learns a nice pose prior. There are other ones. There's a nice paper on normalizing flows for learning this by Schmidt-Chinescu's group. You can learn pose priors in a bunch of ways today that are really pretty nice. And typically you don't want to just model per joint. You would like to model correlated pose across the whole body.
There's a very common question asked multiple times, which is, what's the intuition behind using rotation matrices? Is there any intuition for pose correction? And why did the joint angles, raw joint angles, didn't work?
It's a good question. So there is a problem with the joint angles going from negative numbers to positive numbers. It's just a little technical issue. And that's one of the things that can cause collapse, like here where the neck. It depends on how you set them up. It turns out that the elements of the part rotation matrices is not absolutely critical, because Ahmed is using unit quaternions, and that works just as well. Ahmed, do you want to comment anymore?
Yeah, so just as well, like the joint angles. So if you go beyond 2 pi, say you just keep rotating the joint with the row joint angles, this is just new area in space. Under the rotation matrices, you're still being mapped because it's cosines and sines, it's cyclic. So this is it has a more desirable properties. Yeah.
Any comment on quaternions, or you save that for later?
Oh, the quaternions, I'll talk about it in the later about stars. So we apart from the fact that it's a more compact representation compared to the rotation matrices. So instead of each vertex being regressed from 207 numbers that you talked about, the quaternions is just a lot more compact and generalize better.
It was actually a suggestion of one of the reviewers of the original simple paper to use quaternions instead, and it would do the same. Thanks. Reviewers are sometimes very helpful. Okay, we should, I'm just checking my watch. So now we have this shape space. I mean, we have the pose now represented. So we have something that adds correctives for pose for a single shape. Now to add, we're just going to add in our blend shapes for body shape. These are the principal components controlled by the small set of parameters beta. And here you see it's completely additive. It's a template plus the shape correctives and the pose correctives. And the shape contribution BS here is just a linear combination of, I called them U before, but here they're called S, which are the eigenvectors of the shape space. Okay, and then for the joints, we need to get these joints in some way, and we learn a joint regressor, which is a sparse matrix that looks at vertices in the body and estimates the joint locations as a linear combination of this sparse number of vertices, sort of highlighted here. You can look at the knees, you can kind of see a bunch of vertices being used to do that. So Then the final model, it looks like this expanded out for a single vertex, TI. You add some displacement for the shape, you add some displacement for the pose, which is a function of the pose. You do linear blend skinning, and you get a vertex out. And because this is all built on linear blend skinning, it's compatible with graphics packages. And the nice thing here is everything's going to be trained from data, which makes it accurate. So the model has a bunch of parameters. The template mesh, I told you the topology of the template mesh is designed by an artist, but the shape of the template mesh is learned. The blend shape matrix is learned with PCA. The pose blend shape matrix is learned by fitting it to data. The blend weight matrix is learned, and the joint regressor matrix is learned. So all of these things are going to be learned by minimizing the Euclidean surface reconstruction error given this training set of body poses that we have. So there's a bunch of regularization that has to happen to make this work. So the pose blend shapes, the blend weights, and the joints are trained using this 1800 pose data set. The pose blend shapes are regularized towards 0 so that they don't go crazy, to make them a little bit sparse. The joint regressor is regularized to predicting joints near the boundaries between the parts, and it's regularized to be sparse. And W, the blend shapes, is regularized towards an initial set of artist design blend weights. I'm sorry, blend weights are regularized towards an artist design blend weights. And very few people have successfully done this. A couple of them are on the call. Ahmed is one of them, and it's actually kind of a hairy process. Not the easiest thing to do. But the final thing looks like this. Because everything is learned to minimize surface to surface error between simple and the scans, it ends up looking pretty good. Here's the different body shapes doing the same motion, and they should look pretty natural. Okay, so that's simple. Now we'll come back. Now that you know that, I'll come back to the question from earlier, which is what about pose variation? So these 3 women are all standing in an A pose, but you can see that their posture is really quite different, and there's a lot of variation in pose. And in many of the early models, you see this. If you look at the principal components and you haven't factored out pose, some of the first principal components will be, the arms moving in and out, okay? So you don't want that. The way we pose normalizes the following. It's a 2-step process. Before we know the shape of the body, we have these registered meshes. Those are the V's here. And what we do is we take a generic template mesh and we optimize for the pose of that mesh such that it minimizes the difference between the edges of the mesh we're optimizing and the registration. And this is kind of body shape neutral. It tries to get the pose right. You're really trying to get the angles of everything right. And so it gets the pose and ignores the body. Once we've got the pose of that particular registered mesh, like each of these women, we keep that pose fixed, and then we optimize for the template T that minimizes the squared difference to the vertices of the registration. And the reason I didn't tell you this before is because it actually depends on having a model. Because we have the pose-dependent deformations BP in here, which are a function of the pose of the body, and the joint regressor J, which is a function of the shape of the body. So obviously, you need this unposed. You need to unpose to learn the model in the first place, and you need the model to do the unposing. And so we're back in that chicken and egg problem I mentioned before. So you want to iterate this process or try and optimize it in a joint way. It's probably a little too dense. I apologize for that, but hopefully it answers the question about pose normalization. It's an absolutely critical step. Okay. I am going to skip over soft tissue just for the sake of time, because I've got 6 minutes before we really have to get on to the next talk. So SMPL's been pretty popular. It's widely used in academia and industry, but it's not enough. We interact with the world and each other through our hands and our faces. So then we built a model SMPL-H for hands, and then SMPL-X for hands and face. X stands for expressive. And if you want to call it simplex, that's also fine. SMPL-X or simplex both work. To do this, the scans we've talked about so far didn't have detailed faces and hands. So we captured separately high quality face scans. We use the 3800 head scans from Caesar to get a wide variety of head shapes. We captured a bunch of our own 3D, 4D scans of heads doing extreme expressions. We use a total of 33,000 scans in total. And then we do exactly what I said for SMPL, and we learn a shape space. We factor out pose in the same way. We learn a shape space. We learn a pose-dependent deformations, see nice neck rotations, jaw rotations, and so on. And then we also factor out expression, and we learn a linear subspace, again, linear, for expression variation. We've also explored all kinds of nonlinear models. For example, our COMA work uses mesh convolutions to do this in a nonlinear way, but then it's not compatible with standard graphics packages. So this is the linear flame model, which can be used either together with SMPL-X or independently as a head model. All right, I'm gonna skip over this. We did the same thing for hands. We scanned 2018 hands, left and right hands of 31 subjects interacting with objects and using a well-established protocol. We brought them all into registration again, aligned them, and then put them into a canonical pose and solve for the principal components. Every time the background color changes, you're looking at a different principal component, and then solved for the blend shapes again, and you can regularize these to be local. So this is just illustrating the influence of different blend shapes on the hand pose. So with those two things, I'm not going into great detail here of how we put it all together. We came up with SMPL-X, which is expressive, and you'll see more about that when Dino and Dimitris talk. It has more parameters, of course, than SMPL because it has the expression parameters for the face, the jaw, and the hand parameters. We have low dimensional spaces for hand pose and the facial expressions. And because there's a unified body space, one tends to use more than 10 principal components that people use in SMPL because there's more detail in the face and you need more principal components to represent the body and the face together. Okay, that's a whirlwind picture of SMPL-X. So there's a whole family of models: SMPL-H with the hands, SMPL-X with the hands and face. We have male versions of each of these, female versions of each of these, and a gender neutral one, which is useful for many computer vision applications. We also have a dimple model, which I skipped over today for lack of time, shown on the upper right, which is a soft tissue model, which captures soft tissue variation quite realistically. That's distributed with the regular SMPL release. We have Smile, which is an infinite model shown in the middle, which is very cute. I love it. And then we have and Small, which is an animal model, which is based on SMPL as well. It's got a PCA space and pose correctives and all those things. Actually, linear blend scanning, I don't think there's pose correctives. I don't think so. There's a bunch of other things out there now. Following on from this, Ahmed will talk about STAR later, which fixes a bunch of problems with SMPL. Google has a model called GOOM, which is very similar in the design to SMPL, but replaces a lot of these linear bits with nonlinear ones. You can check those out. I get a lot of questions about licensing SMPL. They are available for research purposes, all of these models. Commercial use requires a license, and it's easy to obtain that from meshcapade.com. Lots of companies have licensed it. I don't know how many now, but a lot. So it's easy to do. It's a little confusing to people. There's two models, two licenses out there. There's something called simple model. This you need to create bodies. This includes the shape space, i.e. these betas. So if you're doing something commercial, you need this, and you're creating bodies, you need the simple model license. Once you've created those bodies and the shape space is gone, you just have a fixed template. Then the pose correctives and everything is covered by the simple body license, which lets you freely distribute created meshes and poses that anybody can use and animate. We think of this as like PDF for bodies. So in the same way you might have an Adobe product to create your PDF file, once you've made your PDF file, you can give it to anybody and they can do whatever they want with it. It doesn't require a license to use the PDF file itself. If that's not clear, we could talk about it later in the discussion. So finally, I need to tell you about how do you animate simple. Often people use motion capture to get a skeleton and then they try to animate from the skeleton. This doesn't work very well. So a key piece of technology you'll hear about later is Mosh, in which we fit simple directly to the mocap markers. In this case, there's only like 40 mocap markers, so very, very sparse. But simple provides a very strong prior and about what the body shape could be. And so we fit it directly to the marker data and get out very nice, highly realistic animations. We use this to create the amassed data set, which is about 45 hours of mocap data, which unifies many of the mocap data sets into a standard format in simple, which people are finding pretty useful, including ourselves. So now just a few teasers for CVPR. This idea of representing the body by its surface, we really pushed this in a project called Mojo, which is about predicting human motions from past motions, and it focuses on estimating a sparse set of markers and projecting it into space of valid bodies. It works pretty well. Of course, there's a bunch of other avatars out there in the world today. The most exciting new one is the MetaHumans work, but all of these lack a realistic human shape space like Simple has. And so that makes it problematic for creating lots of people with realistic body shape variation. But I think you'll see some interesting work about putting these kinds of things together. And then where's the field going? There's a lot of interest in moving away from meshes in the computer vision community towards latent representations of occupancy or assigned distance functions, et cetera. To moving away from this explicit factoring towards maybe automatically learning to disentangle. You might need more data to do that. And learning 3D shape from 2D, because there's just, as we've talked about, a very limited amount of scan data in the world. So if you could learn from 2D data, it would be great. And also moving away from classic graphics and meshes towards some form of neural rendering. So there'll be a talk later on this, so I'm not going to go into it, but here's an example of neural rendering combined with simple to create relatively realistic motions of people doing something that they never did. Simple neural rendering. And then there are a few more papers at CVPR that are worth paying attention to. Scanimate is, and Scale are representing bodies and clothing. Both of them exploit simple, and the posing of these models is all based on simple. It's very common in the field right now to use simple as a backbone for implicit surface modeling. Also, the paper LEAP is basically an implicit version of simple based on occupancy. It works really nicely, and it can be extended to other things. And then a paper from some folks that work with Gerard Ponsmoy, which I thought was pretty cool, Simplicit, which is building some implicit clothing on top of simple. So there's a bunch more papers, and I'm not going to go through them. All of this will be on the web, and including lots of pointers to resources and so on. So skipping the video portion, the data set portion of the presentation, we are now 3 minutes behind only, which isn't terrible. How, do we have any questions that we should?
We've covered a few on the chat, but yeah, go ahead, Ahmed.
So there was a question, yeah. So through pose variation, is there any conservation of absolute location of mesh vertices? For example, if a mesh vertex, if mesh vertices were by a human associated with a shoulder in two different poses, upon translation back to the template T-mesh, would both sets of vertices be the same?
Yeah, yes, that's critical. It's the fundamental assumption that allows this all to work, that the bodies are in correspondence. So this is why we work so hard on the registration part, so that a point on the tip of the nose is the same vertex on every person, and the same for the shoulder. Of course, it's a little ambiguous exactly where things are on the shoulder. So in some of our work, we use texture patterns on the body. I had to skip over that for lack of time. But when we can put texture on an individual, then at least for that individual, we know what corresponds in every scan very precisely. Across people, it's a little harder, but we try very hard to make sure that people are in good correspondence.
The key to that is good registration. So if you've registered such that there's no sliding,